Yeah, so my talk today is going to be essentially looking at a problem in deep learning and trying to take a perspective that maybe comes from operations research to develop new methods to solve it. So this is the kind of a series of papers that we've been working on over the past couple of years with my co-authors, Ross, Bochuan, Will, Krunal, Christian, and Juan Pablo. Okay, so just to make sure everybody's on the same footing to start out with, I'm just going to describe what a piecewise linear function is, right? It's a quite simple object. The idea is that you have some function, you have a partition of the domain of that function into pieces, and then your function is going to be linear on each of those pieces. But the linear part can vary as you move across these different domain pieces. So these are, in some sense, a very simple family of functions. They're kind of locally linear. But they're nonetheless capable of articulating really complex nonlinear or non-convex kind of behaviors. And piecewise linear functions arise in a lot of contexts in OR. And in fact, I spent a lot of my time during my PhD thinking hard about kind of how best to model and solve optimization problems containing piecewise linear functions. So in OR, you might encounter a piecewise linear function to model something economic. Right, so maybe you have some diminishing returns or economies of scale that arise. If you're working in process engineering or chemical engineering, right, you're working with a physical system. Maybe you're mixing some chemicals together and they interact in a nonlinear way. Right, so it's natural to try to capture these nonlinear behaviors through a piecewise linear approximation. And so often in OR, we get kind of lucky, or we take some modeling assumptions such that we work with low dimensional or separable piecewise linear functions, which is quite nice from kind of an analytic perspective. So there's kind of a long sequence of work spanning decades, developing really good algorithms for solving these types of optimization problems, particularly looking at this kind of low dimensional setting. So I picked out two pictures here from my PhD thesis. I spent a lot of time thinking about univariate piecewise linear functions like we have here on the left, and then bivariate piecewise linear functions like we have over here on the right. Right, so these are low dimensional, and you can really throw tools like polyhedral theory at them to understand how best to model them in an optimization context. Okay, so that's some background on piecewise linear functions. We'll return in a second, and now I'm going to tell you about the application in deep learning that we're kind of targeting. And this is neural network verification. So the idea is that it's been observed over the past couple of years that you might train a neural network that has really good accuracy in sample and out of sample, but is nonetheless vulnerable to what are called adversarial attacks. And I think the idea is best illustrated through a picture, right? So we can look over here at a panda. We've trained some image classification network, and our network agrees with us, right? It says that this is a panda. And then an adversary comes along and it adds what looks really like random noise to this image and produces something that, as humans, we look at and say, okay, this is still a panda, but it is going to confuse our model, and our model is going to misclassify this image, right? So it's kind of made this really targeted local change, a small local change that has really confused our network in some way. And so this vulnerability is potentially quite dangerous, particularly if you're trying to deploy this network in a mission critical system or there's not a human in the loop. And so this has been a kind of a really popular area of machine learning research recently, trying to understand, okay, how do we try to mitigate this vulnerability? How do we detect when a network might be vulnerable to an adversary? And so that's what the neural network verification problem is, essentially. So we can model this as an optimization problem. One way to think about this is you take some reference image. Maybe we take this image of a panda here, and we draw a little L infinity ball around this panda, and then we search over that ball to try to find kind of the worst case adversarial instance. So we look and we try to maximize the difference of the probability that we misclassify, or a network misclassifies this perturbed image, and against the probability that it correctly labels it. So kind of on the primal side, right? So if we think and we can come up with a feasible solution where this objective is large, we have come up with an image under which our network is doing something very undesirable. And so this might be useful in, for example, adversarial training. On the dual side, if we can verify that this objective value is quite low, right, then we verify that our network is robust, at least in kind of a local sense. So the key insights, the thing that we're kind of trying to do here in this line of work really stems on the following simple observation, which is just that a trained neural network using standard activation functions is just a big piecewise linear function that's built up through composition. And so we can think of this neural network verification problem as a piecewise linear optimization problem. And our ideas, or our kind of approach here, is to try to take the techniques that you might encounter in OR, things like polyhedral theory, and apply them to this particular application to derive good algorithms. Okay, so we have a sequence of papers over the past couple of years, and really what I want to emphasize at this point is I want to take a moment just to say that this is somehow a more general setting than what I've described, right? So I'm going to talk particularly about neural network verification, but really what we're doing is building methods for solving optimization problems over a trained neural network. So kind of a generic picture of what I described previously, it might look something like this, right? So we want to maximize the output of a neural network subject to some constraints on the inputs. And this might be hard for a number of reasons, right? Maybe our neural network is typically going to be non-convex, and maybe our constraint set is complicated in some way as well. Okay, but I also want to consider maybe a broader class of problems, right? So let's just consider a generic objective function f that we want to maximize over some domain. And maybe we don't know what f is, right? Maybe f lives out in nature, and I have no hope of ever knowing this analytically, right? So how do we think about solving something like this? So one thing you can do is to try to borrow ideas from supervised learning, right? So you say, I don't know what f is, but I've observed it act in the past, right? I have historical data of inputs and outputs to this function. So I specify some family of models. I take my data and I run a learning algorithm, and I fit some approximation of this thing that I do not know. Okay. I want to emphasize a subtlety here, which is that our optimization problem, really, we were trying to pick out a single point. Typically, when you think in supervised learning, you think more in terms of generalization, right? So you care about the behavior of your function with respect to some distribution, not with respect to just a single point. But so this is I think, a reasonable way to think about this problem in some settings, where you don't know what f is, you want to solve this problem, and then you take historical data, you train a proxy model, and then you just plug it in place of f. So now this is a deterministic optimization problem. We know exactly what this neural network approximation is. And so you might encounter this type of approach in, for example, deep reinforcement learning. So think of Q learning, right? So the idea is that you have some Q function which takes a state of the world and takes a potential action, and it kind of computes the long-term reward that you might garner. Okay, and this object in general will be quite complicated. You may not hope to know what it is, but you might have observed historical samples, all right? And you can take the data and train a neural network approximation. And then when you actually want to try to come up with a good policy, right, you can solve an optimization problem over this particular neural network approximation. There's another, I think, nice example that comes from sequence design, right? So there's a series of papers from 5 or 6 years ago where they're looking at building neural network or deep learning models for predicting whether given sequences of DNAs will bind with particular proteins, right? So you have a predictive model, let's say input sequence is likely to bind or not likely to bind. And one thing you might want to do on top of that is actually come up with potential candidate sequences that you then take to a lab and synthesize and actually verify, right? And maybe you want to do this in the context of drug discovery, right? You're trying to design a pharmaceutical product. Okay, so how do we actually solve these problems? There's a whole host of algorithms that you might try to apply here, right? So you might look on the primal side, run something like gradient descent. You might run a cross-entropy method or a genetic algorithm. If you look on the dual side, you can run something like interval arithmetic. Maybe you write down a linear programming relaxation or a semi-definite programming relaxation. Later on, we're going to look at a linear programming approach to this problem. But for the moment, we're going to focus on mixed integer programming, which is kind of an exact method for modeling these problems. And it's nice in the sense that it brings together both the primal and the dual side into one framework. Okay, for this audience here, I'm not going to belabor this one slide on background of neural networks, but I think that there's one key point here that I want to hit upon. So let's just consider a standard feed-forward network, right? You have a series of layers, and in each layer, you have a set of neurons. And what those neurons do is they take the values, the output values from the preceding layer, they apply some affine transformation, and then they plug that value into an activation function, for example, the ReLU function. Okay, and so what we're doing here is we're composing affine functions with a piecewise linear function if you're using a ReLU, and you're doing this in a networked way. And so really what you end up with at the end of the day is a neural network that is just a big piecewise linear function built through composition. Okay, so I'm also going to give you some backgrounds on mixed integer programming, mostly so we have some terminology for understanding kind of the contributions of this work. So what I want you to think of here is that mixed integer programming is really a framework for modeling non-convex things in optimization problems. So imagine that we want to model this set of 3 red lines, this non-convex set. So what we can do is we can introduce auxiliary variables, and then we build a polyhedron in this extended space. So we have our original variables, we have these new variables that we added, and we build some LP relaxation or polyhedron in this extended space of variables. And what we want is when we take that polyhedron, we intersect it with integrality on these new variables that we've added, and then project them out, that we recover our original non-convex set. And so we potentially have a great deal of freedom here in crafting what this polyhedron looks like, what our integer variables, these auxiliary variables, do in some sense. And so what we want is to try to understand what makes one formulation better than another one. And so we have a couple different ways of trying to assess that. One is just looking at the size of the formulation, right? So how many variables and constraints do we need to write it down, right? Smaller formulations typically are better. Another way is trying to understand the strength of a formulation. So I think that's maybe best understood by looking at pictures, right? So we have 2 potential formulations here side by side, or rather the projections of those formulations to the original space. And intuitively, we should understand that this thing on the right is going to be better. It's tighter. It actually gives us the convex hull of these red lines, the things that we are trying to formulate, right? And so we'll get better bounds out of this, and this will perform better in the branch and bound setting. Okay, so this formulation over here on the right is what's called sharp, right? It recovers the convex hull of the red lines. We also have a notion of what's called hereditarily sharp formulation, which essentially means that you retain this sharpness property throughout the branch and bound tree. And the holy grail, the best you can hope for, is what's called an ideal formulation. And this is a statement about the extreme points of your LP relaxation. And this is really the best you can hope for in terms of strength. It implies sharpness, this other property. And so this is what we're going to be shooting for in the context of this work. Okay, so I can summarize maybe the most important theoretical result in this small table here. So a neural network is built compositionally, right, through simple operations. And we're going to do the same thing for our MIP formulation approach. So we're going to look at each neuron in our network individually. We're going to formulate it as best we can, and then we're going to compose each of those formulations for each neuron together. Okay, and what we have here in this table here are 3 approaches, 2 of kind of standard techniques and 1 in the middle, which is our new approach. So you can try to use the big M approach, which is kind of a standard technique for each neuron. And this is quite nice in the sense that the formulations are going to be small. Unfortunately, they're not strong, right? So they're not a sharp formulation. On the other end of the spectrum, you have a disjunctive or abolish approach, right? So here, the formulation is ideal, so it's quite strong, but unfortunately, the number of variables that you need to write it down is quite large. So our new formulation, our new approach sits here in the middle, and the idea is to try to blend the best of both worlds. So we have a small number of variables that we need to write it down, and it's sharp, and in particular, it's ideal when we're working with activation functions with 2 pieces, namely the ReLU. Okay, so let's look in a bit more detail about how this formulation is actually going to look. So we're going to focus on a single ReLU neuron. So we have inputs X. These are multivariate inputs. We have a single output Y, and we have weights and biases, right? So we apply some affine transformation to the inputs and then apply our activation function, the ReLU. And crucially, we're also going to have bounds on the inputs. So think of the first layer, right? If we're looking at this verification task, the bounds come from us taking that target image and writing this L infinitely ball around it. Okay, and then if you go to later layers, you might have run, for example, interval arithmetic to compute bounds in the inputs. And what we're going to do is we're going to wrap up all the pairs of feasible inputs and outputs in this set here, which is called the graph, right? So we take feasible input X with respect to the bounds, apply our affine transformation and the activation function, and set Y equal to that output. Okay. And like I mentioned in the preceding slide, there's this standard big M formulation approach, which has been used in the literature in this context a number of different places. And it's quite simple, it's nice, it's compact. But like I mentioned, it's not strong. And we can see that pictorially. So we're looking here at a simple two-dimensional input, ReLU neuron. And on the right here, we have the convex hull, right? So this is what you would get with a sharp formulation. And on the left here, we have what you get from the big M formulation. And so in particular, we notice that there's a fair amount of slack here, particularly on the corners. Okay, so the bounds coming from this formulation will be worse. So our first contribution here essentially is a characterization of what inequalities we need to add to this big M formulation to recover this convex hull. And the real meat of it comes from this large family of inequalities here, 1b. So essentially we have one inequality for every subset of the input variables. And so this is an exponential number of inequalities. And moreover, you can show that under very mild conditions, you actually need all these inequalities to recover the convex hull. Okay, so this seems unfortunate, right? We have a formulation which is large in terms of the number of constraints that we need to write it down. But the nice thing is that the separation problem over this large family can be solved efficiently. So we can solve it in linear time. Another thing that's important here is that the big M formulation, this one that's been used in the literature, is kind of hidden here, right? So algorithmically, what we're going to do is we're going to write down that big M formulation, and then we're going to dynamically generate cuts from this large family as we need them in a cutting plane approach. And we developed kind of a whole framework that applies not just to the ReLU. You can also use it for other types of nonlinearities that you might encounter in a neural network, right? For example, we can model max pooling or reduce max operations, kind of using a similar technique. So what we have here is a formulation that applies kind of generically for any box input domain, and then an activation function, which can be described as the maximum of D affine functions. So max pooling, reduce max, so on. This formulation is hereditarily sharp. It's not necessarily ideal. And again, the magic is really in this large family of inequalities that upper bounds Y, upper bounds the output of the neuron. And again, the separation problem over this family of inequalities can be solved efficiently. Okay. And like I mentioned, we have this whole framework for generating these formulations for kind of arbitrary inputs, arbitrary affine functions that describe the output. I'm not going to belabor the details too much. Essentially, we start with this Balash extended formulation and do some manipulation, apply a Lagrangian relaxation, and then do a bit more analysis afterwards. Okay, so let's look now at the computational results. So what we have here is a small network that was trained to classify MNIST digits. And we're comparing three methods. So we're comparing the big M formulation, the extended formulation, and our new method in blue. And the way to understand this chart is that things to the top left are better. They solve more instances more quickly. So what we see here is that our new method dominates the other two approaches. It's able to solve more instances more quickly, which is nice. The kind of unfortunate thing here is that, like I mentioned, this is a relatively small network. And if you look, we're still not able to solve all of these instances to optimality within the time budget. So one way of understanding why this might be the case is that the network that we trained here is almost completely dense, right? And so we end up with a mixed integer programming formulation that is very dense and difficult to solve. So one thing that you can do here, Tiago mentioned this in the preceding talk, is you can try adding L1 regularization, right? And so this will induce sparsity in the weights, and this ends up helping pretty dramatically improving the performance of these algorithms. So now we can verify all of these instances using our new method in at most 100 seconds. So this is nice. We've gotten a performance improvement, but this is still not going to scale to larger networks. So what do we do? What if we want to go bigger? So one thing you can do is you can try to give up the exact verifier property. So MIP is great in the sense that it will exactly prove or disprove whether your network is robust. But if we relax that MIP, for example, if we use instead just its LP relaxation, then we get what's called an incomplete verifier, which won't lie to you, but might give you false negatives. Okay, so what we did here is we took our MIP formulation, we took these new inequalities, and we threw away the integrality conditions and projected out the integer variables. And we get a description for what this convex hull looks like. And again, the magic is kind of in this large family of inequalities that upper bounds the output y. Interestingly, now this family of inequalities is dependent on the data in some way, where it was not previously. And again, we can solve the separation problem efficiently in linear time.
Joey, you have 5 minutes left there.
Yeah. Okay, so what if we want to go even bigger than this, though? Right. So LP is great; it's going to scale further than MIP, but it's still not going to get you to larger networks. So we can borrow ideas from the literature and try to run what's called a propagation algorithm. So there's been a series of papers over the past couple of years looking at these types of approaches. I'm going to take a kind of OR type spin on it, right? So the idea essentially is that you take your LP relaxation and you relax it even further. So let's look at an individual neuron in the network. And you might have a series of upper bounding inequalities and lower bounding inequalities on the output of that neuron. Okay, and so what we're going to do is we're just going to throw away all but one upper bound inequality and all but one lower bound inequality. So we're relaxing this LP further. But the nice thing now is that we can solve this LP very efficiently through a propagation type algorithm. You can think of this as a Fourier-Motzkin elimination type procedure. Okay, and so what we end up with is an incomplete verifier that we can optimize efficiently. And the wrinkle here, the thing that we're going to try to do that's new, is essentially to use our new inequalities here inside this propagation approach. And so in particular, what we're going to do, we have an algorithm we call fast C2V, is that we first start with a standard choice of these upper and lower bounding inequalities. We propagate, we solve we get a verification bound. And then we take our input point and we propagate it forward through the network. And so then we get values at each individual neuron. And then we run our separation procedure at each of those neurons, generate a new upper bounding inequality, and swap that in. Right, so now we have a new series of inequalities for each neuron, and then we can run our approach again and produce what is hopefully a stronger verification bound. Okay, so we can look at some computational results. So we're trying to compare like methods with like methods. So we have fast C2V, this is the propagation method I just described. We're comparing it against deep poly, which is a state-of-the-art propagation method. And we can also have op C2V, which is this LP with cuts method that I described, and we can compare it against the vanilla LP relaxation. And essentially what we see here, the story, is that by using these new inequalities that we've derived, you can produce tighter verification bounds, which means that you can verify more instances. You end up paying a bit more in terms of the computational time that you need, but it's usually, let's say it's roughly on an order of magnitude, sometimes more, sometimes less. Okay, and another thing that I want to highlight here is that particularly on these larger networks over here on the right, the gap, the difference between fast C2V and op C2V gets smaller, right? So somehow for these larger networks, it appears that the propagation-based method is capturing most of what's going on in the full LP, but it's running much faster. Okay, so at the end here, I just want to briefly mention some ongoing work that I'm doing with my graduate student, Bochuan. We're looking at a different type of architecture here. We're looking at binarized or quantized networks. So the idea here is that modern neural networks are typically quite big, and they're not going to necessarily work great on small devices like an Apple Watch. Okay, so one thing you can do is try to make an observation that, in some sense, if you're using floating point numbers to model each weight or activation value, this might be a little bit wasteful. So the idea behind a binarized network is essentially to replace all those floats with binary values, plus or minus 1. So you're losing a lot of granularity there, but you're reducing your memory footprint quite substantially. And a quantized neural network essentially is saying, okay, maybe we won't just use 1 bit, we'll use a handful of bits for each of these values instead. And it's interesting, the verification problem becomes quite different in this setting, right? the activation functions are now discontinuous. You have jumps in them, and you have to think about how you model those for the verification problem. It's also not clear how good the convex relaxations that you get are when you have these jumps. And so you can play the same game where you try to derive strong inequalities to recover the convex hull, but they might not be great for you at the root node, right? They might still be useful algorithmically, though. So in particular, you can use them later on the tree to induce what's called consistency, and this will help you guide search and reduce backtracking. So I want to thank you for your attention, and I'd be willing to entertain any questions you might have.